ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಕಳೆದ ವಿಡಿಯೋದಲ್ಲಿ ಇನ್ಸಿಡೆನ್ಸ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಅಂಡ್ ಅಡ್ಜಸೆನ್ಸಿ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಬಗ್ಗೆ ತಿಳ್ಕೊಂಡ್ವಿ. ಸೊ ಗಿವನ್ ಎ ಗ್ರಾಫ್ ಹೌ ಟು ರೈಟ್ ದಿ ಇನ್ಸಿಡೆನ್ಸ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಅಂಡ್ ಅಡ್ಜಸೆನ್ಸಿ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಅಂಡ್ ವಾಟ್ ಆರ್ ದಿ ಪ್ರಾಪರ್ಟೀಸ್ ಆಫ್ ಇನ್ಸಿಡೆನ್ಸ್ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಅಂಡ್ ಅಡ್ಜಸೆನ್ಸಿ ಮ್ಯಾಟ್ರಿಕ್ಸ್. ಈ ವಿಡಿಯೋದಲ್ಲಿ ರ್ಯಾಂಕ್ ಆಫ್ ಎ ಗ್ರಾಫ್ ಅಂದ್ರೆ ಏನು ಇದ್ರ ಬಗ್ಗೆ ತಿಳ್ಕೊಳ್ಳೋಕೆ ಹೋಗ್ತಾ ಇದೆ. ಸೊ ಐ ಹ್ಯಾವ್ ಎ ಗ್ರಾಫ್ G. I can write the adjacency matrix and also I can write the incidence matrix. Adjacency matrix will be of order n cross n, where n is the number of vertices in the graph. Incidence matrix will be of the order n cross m, where n is the number of vertices and m is the number of edges. Now you have matrices. Given any matrix, you can find its rank. Now I can define the rank of adjacency matrix, that is denoted by rho of A of G, and rank of incidence matrix. So for our discussion here, we are going to consider this parameter only. This I am not going to consider. The rank of the graph we are going to define as the rank of the incidence matrix of that graph. So I have a graph G. The rank or incidence rank of that graph, actually incidence rank anta helbeku. So illi ನಾವು ಬರೀ ಇದೊಂದೇ ಪ್ಯಾರಾಮೀಟರ್ ಕನ್ಸಿಡರ್ ಮಾಡ್ತಾ ಇರೋದ್ರಿಂದ ಬರೀ ರ್ಯಾಂಕ್ ಅಂತ ಹೇಳ್ತಾ ಹೋಗ್ತೇನೆ. So the rank of a matrix, rank of a graph G is the rank of incidence matrix of that graph. That is the definition of rank of graph. Now, given any graph, we can find the incidence matrix of that graph. Then, applying elementary row operations or column operations, you can find its rank. So it is not always possible to apply elementary operations because we are going to consider graphs of use order or use size. So sometimes you may get a graph of order 5. Order may be less, but sometimes size will be greater. If you take a complete graph, size will be any 10 minus 1. Even if you take n 4 or 5, you get huge size. So there is one theorem that helps to find the rank of connected graph. If G is connected, if the graph is connected and of order, or simply if G is a connected graph of order n, then rank of G. Simply we will write a rank of G. Not necessary to write rank of I of G. So rank of G will be n minus 1. So if G is a connected graph, then its rank will be n minus 1. For example, if you are asked to find the rank of K5, what is the rank of this graph? So K5 is a connected graph. We know it is a connected graph. So the rank of this graph will be 5 minus 1. What is 5? 5 is the number of vertices, order. So rank of K5 we can directly write, that is 5 minus 1, 4. If you are asked to find the rank of C cycle on 50 vertices, you can't write the incidence matrix, then its rank. You can directly apply this theorem. The rank of C50 is 49. So that theorem helps to find the rank of connected graph. Unless you have connected graph, you can't apply this theorem. So for the statement says if G is a connected graph of order n, then rank of G equal to n minus 1. So this is some basic results about incidence matrix and adjacency matrix of the graph. Now we have a new type of matrix. So totally we have 4 types of matrices. Out of 4, the third one, circuit matrix. Circuit matrix. We have already defined what do you mean by circuit. So ಯಾವಾಗ ಡಿಫೈನ್ ಮಾಡಿದ್ವಿ, ಕನೆಕ್ಟೆಡ್ನೆಸ್ ಹೇಳಬೇಕಂದ್ರೆ ಡಿಫೈನ್ ಮಾಡಿದ್ವಿ. ಸೊ ವಾಕ್ ಅಂದ್ರೆ ಏನು, ದಟ್ ಈಸ್ a sequence of edges and vertices. Walk is just a sequence of edges and vertices. Usually the end members or end points will be vertices. If in a walk all the edges are distinct, then it is called trail. If in a walk all the edges are distinct, then it is called a trail. If that trail is closed, that means end vertices are same, closed trail is called a circuit. closed trail is called a circuit. Here I have the graph. Now first I have to identify the circuits in this graph. Before going to write the circuit matrix of the graph, first you need to identify what are the circuits here. So I will start with this. I will start from this vertex. This edge A, again edge B. That forms a closed trail. Edges are distinct. So that is a closed trail. So first circuit. C1 equal to A comma B. Next, you just identify the region bounded by different edges. ಅಷ್ಟೇ ಬೇರೆ edges ಇಂದ ಕವರ್ ಆಗಿರೋ ರೀಸನ್ ಐಡೆಂಟಿಫೈ ಮಾಡಿ. ಇದೊಂದು ರೀಸನ್, ಅದೇ ರೀತಿ ಇಲ್ಲೊಂದು ರೀಸನ್ ಬರುತ್ತೆ, ಇದೊಂದು ಬರುತ್ತೆ, ಓವರ್ ಆಲ್ ಒಂದು ರೀಸನ್ ಬರುತ್ತೆ. ಸೊ C1 A comma B, C2. C2, let us consider this one, this region. So here the edges are E, G, C. Or you can write it in order. C, E, G. C, E, G. Next, C3. This one. Here it will be F, D, G. So order ಬಂದ್ರೆ D, F, G I can write. D, F, G. C4. This bigger one. C, D, E, F. Order ಬರ್ತಿದೆ ಅಷ್ಟೇ. C, D, E, F. ಇನ್ನು C4. So these are the four circuits of the graph. Now I have four circuits and there are totally 1, 2, 3, 4, 5, 6, 7, 8 edges. There are 8 edges. So given a graph G, given a graph, a matrix, the circuit matrix is given by, is defined by B of G. Usually B of G and the circuit matrix ke B of G equal to Bij, where Bij will be 1 if ith circuit includes jth edge. If ith circuit includes jth edge, otherwise it will be 0. Otherwise it will be 0. That is the definition of circuit matrix. So here I runs through the number of circuits, J runs through number of edges. So order of this matrix will be number of circuits. For example, K and K, number of circuits cross number of edges, EM. K denotes number of circuits in the graph. So order of the circuit matrix will be number of circuits into number of edges. Now let us write the circuit matrix for this. Okay, B of G equal to so rows represents circuits. So C1, C2, C3, C4. Columns represents edges. A, B, C, D, E, F, G, H. Now C1 A. So C1 A ಮತ್ತೆ B ಇದೆ. A ಮತ್ತೆ B ಇರೋ ಕಡೆ ಮಾತ್ರ ಒಂದು ಬರೆಯಿರಿ. A and B are included in C1. So A ಮತ್ತೆ B ಗೆ 1 ಬರೀತೀನಿ. ಉಳಿದ ಯಾವುದೇ ಎಡ್ಜು C1 ಅಲ್ಲಿ ಇಲ್ಲ. So 0 0 0 0 0 0. ಅದೇ ರೀತಿ C2 C E G C E G C E G. ಇವು 3 ಮಾತ್ರ C2 ಅಲ್ಲಿ ಇರೋದು. ಸೊ ಉಳಿದೆಲ್ಲ 0. Now C3 D F G D F G. So ಉಳಿದದ್ದು 0. Now C4 C D E F C D E F. So remaining are all 0. So this is the circuit matrix of this graph. Circuit matrix of that graph. Now let us have some observations on the circuit matrix of the graph. So now look into the entries of circuit matrix. Obviously this is a binary matrix, so entries are only zeros and ones. Observations. Number 1, B of G is a binary matrix. Number 2, if you take a row sum, here sum 2, here sum is 3, here sum is 3 again 4. So here 2, there are 2 edges in C1. Sum 3, there are 3 edges in C2. Here sum is 3, again 3 edges in C3. Sum is 4, 4 edges in C4. So row sum gives you number of edges in the circuit, in the corresponding circuit. How many edges are there in that circuit? Now if you take column sum 1, 2, so this gives, see, A is in C1 only, it is not in C2 or C3 or C4. So actually your column sum gives you number of circuits that includes the edge, includes corresponding edge. So in how many circuits that edge is included, that will be given by that row sum. But if we have the H 0 0 0 0 0 column, that means column sum is 0. So here the column sum is 0 means this edge is not included in any circuit of the graph. So if we take 4 circuits, no edge is included here. Yav circuit alli edge illa, so column sum 0. ಇಲ್ಲಿ G column sum 2 ಇದೆ, ಅಂದ್ರೆ G is involved in 2 circuits, C2 and C3. Again C is involved in 2 circuits, sum is 2. So that's about the third observation. Fourth observation, this is as usual permutation of rows or columns or correspond to relabeling of circuits. That means if you interchange any 2 rows or columns here, if you interchange any 2 rows, that actually denotes the relabeling of circuits. ಈಗ ನಾನು ಇವೆರಡು ರೋ ಇಂಟರ್ಚೇಂಜ್ ಮಾಡ್ತೀನಿ, C2 ಜಾಗದಲ್ಲಿ C3 ಬರೀತೀನಿ, C3 ಜಾಗದಲ್ಲಿ C2 ಬರೀತೀನಿ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. If I interchange these 2 rows, that actually represents relabeling of the naming of circuit. ಇಲ್ಲಿ C2 ಅಂತ ಬರೆದಿರೋ ಸರ್ಕ್ಯೂಟ್ ಗೆ C3 ಅಂತ ಬರೀಬೇಕಾಗುತ್ತೆ, C3 ಇರೋದು C2 ಆಗುತ್ತೆ. ಸೊ ಇಲ್ಲಿ ನೀವು ರೋಸ್ ಇಂಟರ್ಚೇಂಜ್ ಮಾಡಿದ್ರೆ ಗ್ರಾಫ್ ಅಲ್ಲಿ ಸರ್ಕ್ಯೂಟ್ ಇಂಟರ್ಚೇಂಜ್ ಆಗುತ್ತೆ, ಸರ್ಕ್ಯೂಟ್ ನೇಮ್ ಅಷ್ಟು ಇಂಟರ್ಚೇಂಜ್ ಆಗುತ್ತೆ. ಅದೇ ರೀತಿ if you interchange columns, then the name of the edge you have to relabel. So edge ಆಗಿರುತ್ತೆ, you have to relabel that name of that edge. So that is about 4th point, that is one of the common point. Again, uniqueness, that comes the next question. Adjacency matrix nodidvi, that is unique. Unique in the sense, if you have a graph that can be uniquely written in terms of matrix. ಅದರದ್ದು ಅಡ್ಜಸೆನ್ಸಿ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಯೂನಿಕ್ ಆಗಿರುತ್ತೆ. ಬಟ್ ದಟ್ ಈಸ್ ನಾಟ್ ಟ್ರೂ ಇನ್ ದಿಸ್ ಕೇಸ್. 5.5 we may have B of G1 equal to B of G2, even they are not isomorphic. That means we can take two different graphs which have same circuit matrix, but that is not true in the case of adjacency matrix. Whenever two graphs are not isomorphic, two graphs are different, their matrices are also different in the case of adjacency matrix. In the case of incidence matrix, that holds in incidence matrix also. In the case of circuit matrix, even the graphs are not same, the graphs are not isomorphic, you may have the circuit matrices are same. So these are some observations about circuit matrix of the graph. Next, one of the important results we have that connects circuit matrix and incidence matrix of the graph. Suppose you have a graph G. Suppose I have a graph G, be the given graph. We will find its incidence matrix and the circuit matrix. Incidence matrix, I will write I of G. It will be of order n cross n, where n number of vertices, m number of edges. Again I can write B of G, the circuit matrix for the same graph. That will be of order k cross m, where k denotes number of circuits. If I take transpose of this matrix, B of G transpose, that will have order m cross k. Now we take I of G, product of I of G with B of G transpose. That will be a zero matrix. Zero matrix, obviously this will be of order n cross k, and 0 under modulo 2. 0 under modulo 2. You don't get exactly zero matrix. It will be zero matrix under the operation modulo 2. Modulo 2 means 1 plus 0 will be 1, 0 plus 1 will be again 1, but 1 plus 1 will be 0. This is modulo 2 operation. Modulo 2 operation. 1 plus 1 will be 0. With respect to this operation, if you take the product of these two graphs, you get zero matrix. So this is one of the important theorems that connects incidence matrix and circuit matrix of the graph.